Hi, all. Welcome. This is our second seminar series of the semester. And I'm very pleased to present Professor Guilherme Melo, who is professor in civil and environmental engineering from the University of Brasilia. He has been there since 1992, where he was head of the civil and environmental engineering department. He received his PhD from the Polytechnic of Central London, now known as University of Westminster, in 1990. His main research interests include punching and post-punching of flat plates and strengthening of RC structures with FRP materials. For almost 30 years now, he's a member of ACI, also FIB and IBRACON, which is the Brazilian Concrete Institute. And he's members of a lot of different committees, has written a lot of papers, and has done a lot of other work, which he would be very happy to share with you. Join me again in welcoming Professor Melo. Thank you very much, and it's all yours. Go ahead.
Thank you, Professor Pranoy. I'm very happy to be here. Good morning to everybody. That's the talk we're going to see today, and let's begin. First, I should acknowledge the University of Miami, of course, Civil Engineering and Architecture Department, Professor Nani, who has invited me to be here, Professor Suraneni, that was very kind in setting everything, of course, the office manager that helped a lot here, and all Professor Nani PhD students. All of them were very helpful with me, especially Zahid. We had some meetings, and I'd like to acknowledge all. As Pranoy was saying, I'm a civil engineer from Brazil. This is my information. I did my PhD in England in 1990. I have supervised quite a lot of PhD and MSc students. I have worked in Brazil at the evaluation of post-graduation course. I have quite some experience on that. And I was for some time director of engineering and science of one of our big research development agencies. And I'm here 6 months at the Miami University. We all know this picture is from a MacGregor book, and it's very good to see a flat plate here, a flat slab, some capitals here, and that's very important for us to try to understand the behavior of that. Here from the same book, we have a flat plate, some waffle slab, flat slab with capitals and so on, and here a two-way slab with beams. Of course, we are interested in this case here, what will behave, what will happen here. It is just to show that because of the difference in the stiffness here and here, for example, we have some even torsion at this size, and this is very important. One example, another, and what we can say. Flat plates, flat slabs are very much used everywhere. It has a lot of structural and construction advantages, small height for multi-story buildings, better ventilations, light, simple formwork, they say, and it is more easy to have a reinforcement of before casting. Some disadvantage, of course, is more flexible, is a more flexible structure compared with a frame, for example, and has the possibility, let's see, of a punching shear failure. And because of that, we can have some progressive collapse, follow a following a punching failure. Then because of that, we should take extra care. Here is our flat plate. We are concentrate in this region here. And of course, you know, big moments in this region. And at the same region, we have a big shear force. Then because of that, we can have a punching failure. This is a crack pattern from a top surface of a 9 columns slab. We can have some cracking in this direction, close to the columns as well. And here we are concentrating in this region around the column. And what happened basically with the loading, we have some crackings, is going till failure here. And what you can see, this reinforcement here, the top flexural bending reinforcement, is very easy taken out here. And someone, if there is a reinforcement here, it can work better. This is basically the surface inclination, and this is a good drawing from the FIB manual saying the cracking before failure, and when goes here through this shell, concrete shell here, there is a punching. This is from the McGregor book, a very nice picture of a punching. And here another one, and it's very important for us to know how it behaves here. Because of this, we have to cut saw the slabs, let's see, when it's possible. Then a punching failure is sudden, without advanced warning, practically without ductility, and for a load smaller than the flexural failure load. It depends on the concrete strength, depends on the flexural reinforcement ratio, on the slab thickness, and on the column dimensions, of course. Shear reinforcement can increase the resistance if effective and well positioned. Here is a model from more than 60 years ago, Kinnunen and Lallander, a very nice model. But of course, there were others. But until today, everybody's trying to find a good model for punching. This is a big conference 20 years ago in Sweden. Kinnunen was there participating and so on. Very important conference. Then another one here, United States, at an ACI meeting, 2005. Then another very important conference in 2017, another special publication at the ACI, honoring Professor Hawkins. And just now, 4 months ago, we had another conference in San Francisco at the conference meeting. I was there. Many students from Professor Nunn were there as well. And everybody trying to understand, to study punching. Shear reinforcement. What would be the ideal shear reinforcement? Of course, effective and requiring simple and easy workmanship. Some are effective, but very difficult to install. Then it's always important to have this in mind. We can say that not all of them are effective, nor simple, nor easy workable at the construction site. And most are positioned before the flexural reinforcement. And then it can bring some difficulties. And of course, good anchorage sometimes is difficult. These are some types the FIB bulletin shows. You can name it a lot of shear reinforcement types. Of course, any one of those should be well anchored and should have the correct length, let's say. Here is an example of a well-anchored reinforcement, shear reinforcement. Of course, it can be in cross or in radial distribution with advantage for either one. And what happened, of course, when you put shear reinforcement, without shear reinforcement, that is the angle of failure surface. If you have, for example, a strengthening here, that would be the difference in behavior. Of course, for a higher load, but changing the surface. That's very important. Basically, we can have then failure inside here, going through the reinforcement and outside the reinforcement. Again, and because of that, all codes have a lot of checking. We should check at this surface if there's no shear reinforcement, at this surface if there is shear reinforcement, the failure could be here, the failure could be here, and the failure could be here. And because of this, we have expression for checking that. Interesting to say that sometimes the load you arrive is good comparing to with the test you did, but the shear failure is not the one that was expected. On the other hand, sometimes the failure surface is what you expected when you test, but the failure load was not. In other words, we have to study much more, everybody, to arrive, possibly in the future, we can know exactly what will happen when the slab is tested. Another important thing here would be for a circular column, how to be the surface itself. And of course, it's more easy for us to use a vertical surface for checking stresses. We have to have this in mind. Here, one interesting from Finland is a kind of UFO, unidentified flying object, looks like. And it's important, but of course, it depends on the size of the column. It will be more difficult to use. Here in the position, here is all the reinforcement, and would need some necking here at the column, and all this should be taken in mind. And of course, this is business. Here is some adverts from the Concrete International. And of course, as we saw, as we noticed, sometimes it's very busy, this region. And of course, anything that can help would be, if it works well, could be good. Another kind of shear reinforcement that we can have, of course, some of them, most of them actually, to be sold, are tested and so on. And we should use one that we have tested, of course, and we believe works. Another one here with shear studs, and can work as well. And then the more traditional ones, of course, can set a kind of a standard and say, oh, ours is best, and so on. That's very important, yes, when you believe, you trust. And of course, I like this because we can't gamble, of course, with anything in structures. Sometimes people are trying to save money, lightening the structure. And of course, it's not a good idea. We should, if we want to save money, save elsewhere in the construction, not at the structure. The structure should be, of course, sound. And another good thing is to think about the post-punching and progressive collapse of slabs. Progressive collapse is a propagation of a failure occurred originally at a small part of the structure, and the result it is proportionally bigger. A good example, it was in England in London in 1968. Maybe all know this example. This is a picture of the building. Then this is at 22 stories. At the 18th story here, one early morning lady was having tea. She hasn't noticed there was a leaking in the gas. Then was like an explosion. She was here at the 18th, and then all the kitchens were going down because it was too early. Only 3 people died at this. I say that because imagine if it was 2 hours later, much more problem would happen. Of course, this is precast, and I like to show this because this was not gas leaking. This was a bomb, but the building could stand for some time, and this is important, of course. And what are the most susceptible structures to progressive collapse? Precast, as you have seen, and flat plates. And there are a lot of examples here, some of those here only at the United States, but we have everywhere. Everywhere that has problems can have progressive collapse. And we're going to show here this in 1981 in Florida. And of course, there was, as you know better than me, one 3 years ago, very close to us here. And in 1981, it was this one in Cocoa Beach, Florida, close to Orlando. And this building was here at the construction. And it was, let's say, a very well-behaved structure in a way, all framed, almost equal spans, here elevator tower, staircase, and so on. And there was a punching deficiency of one of the connections they found later, and then suddenly this was what happened. And this was because of this 18 people dead, 11 dead, and 23 injured. And of course, this can happen. And other examples of punching failures. You can see what's left usually from that. It was in Portugal, other example. All of those pictures I took from internet. It's very easy to find punching failures and progressive collapses. Another one here, you can see that what's left after punching failure is you can see sometimes a failure rupture cone here and some bars just hanging. What could trigger a punching failure and a progressive collapse? Of course, bad design, bad construction sometimes, bad detailing, of course, insufficient punching capacity. Sometimes it happens at the construction time, construction loads. Of course, the materials could be not what was specified. And of course, overload. All of this can trigger. We know that most of the collapses, in general, they have not only one reason. Most of the time, we have some punching capacity not 100%, some construction, some deterioration with time. And what happened, of course, we have a simple example here. when this column, central column goes, for example, or the slab can't hold anymore, this load will go to the neighbor columns, not at the same level, let's say, of load, but of course, then the load and the failure could spread easily horizontally, and of course, could spread vertically as well. One very important, this is a paper very good from ACI as well, showing that is another example of not a failure, but in this case, they could see before because of big deflections and so on. The reinforcement, top reinforcement should be here, and they found, look at that. Of course, this was a problem. And what happened, you can see, if the top reinforcement is at the right position, this would be the load, it would resist. If it's not, the load drops a lot. Then, of course, it's very important to do that. Here is a more recent one, 3 years ago, as you know better than me, and I found in the internet. Of course, they are investigating yet, but this picture shows that this was the cover as designed for the reinforcement, one of the bars, and this in average much more than was designed. Of course, could be one of the reasons that help to trigger, let's say. What would be the aim of a structural design, as we know? Of course, minimize the risk of a progressive collapse. In other words, containing the structural failure. Of course, we all wanted structural integrity, strength, ductility, important, and of course, alternative load path. How sometimes in some structures, you can even design for that. What is a problem happened here? There is an alternative load path, and this is important, of course, because in some structures, would be for all of them, we don't want surprise. And what happened in the post-punching in flat plates? What we know, as we have seen, the post-punching resistance is low, and total or partial failure of the connections. You can have sometimes 10% still hanging there of the load, 20%, or nothing, as we saw. Load and bending moments are transferred to neighbor connections, as we saw as well, and horizontal and vertical propagation of the collapse would happen. And for flat slabs and plates, punching failure is usually the main cause. And of course, with no or small warning. Then, of course, it's very important to take care of that. Then the post-punching, the top flexural reinforcement can be easily torn out of the concrete once an inclined failure surface has been formed. As you saw, this top reinforcement, of course, that is vital for the punching resistance and for the flexural behavior, of course, the structure. After punching, it's easily turned out, as we saw, and they do not resist vertical load. One solution is bottom reinforcement that goes through the column inside and anchored outside. But these bottom bars do not increase the punching resistance, but are effective in increasing the post-punching capacity. And is easy to install. Easy, of course, easy compared to nothing heavy and so on. And then we can see here the top reinforcement is not a good for post-punching, but the bottom reinforcement could help. This again comparing this slab without bottom reinforcement and this is a slab with bottom reinforcement. We can have here, at this case, some 70% of the previous load. Sometimes you can have bigger. And of course, this is important because this, instead of all this load goes to neighbor connections, we can diminish that. Here is just a picture to remember the test I did more than 30 years ago in England to try to understand this and to help with a lot of people in the world. And we tested that. Of course, you can see here, this is the top reinforcement, out of position and so on. And then let's talk about a little of what have been done in Brazil. I'm going to show first here the FRP, because I know that most students here, Professor Nanis, are interested in that. We did some GFRP internal reinforcement, beginning in 1997, some external bonded CFRP shear strengthening, beginning 2000, near surface mounted, beginning 2005, and the strengthening flat slabs 2014, hybrid strengthening beams 2014, and try to find the resistance partials of shear reinforcement later. I should acknowledge here a lot of people, because of course this was a guy very important. He had a company here at United States. He sent us a lot of GFRP bars in 1997, and then Professor Sam Riscala for North Carolina State University. He has been in Brazil and hosted 2 PhD students of us, and sent at that time, a lot of material we could test there. Then Professor Joaquim Barros in Portugal, Professor Eva Oller in Spain, Professor Luc Taerv, Pilacotas, Borgon in Europe. I have is where I met Professor Nani first times at the FRP RCS conference. This some that I went, and some conference in structural fault repairs. These are the list of some of the works we did, beginning also with a undergraduate student, then some master students, then some PhDs, and so on, and the research they did. Here, a picture of a beam to be tested, 4 meters and 400 centimeters, quite a big beam, a T-beam, and some of the shear, CFRP shear strengthening, and some of the results. Of course, it's not so well, and we did there. This material we got from Brazil, this RB, EB sheets CFRP. And here, of course, and then we, as people did, fully wrapped through the flange here. And of course, and then we could reach the maximum load of the strengthening. Quite some peculiar, very good results. Then we did some NSM with CFRPs and GFRP bars and so on. And here were some of the failure we had. Here for the CFRP strip strengthening, and for the CFRP bars, and for GFRPs strengthening. It's very interesting, the results, as you know. We have, of course, published most of these results. And this flat plate strengthening with CFRP fabrics, yes. And this is some of the layouts we use it. And here, two examples of the failure surface. And then let's show now some punch and shear without FRP results. That's actually what worked more. We did a lot in reinforced concrete with stirrups, shear reinforcement, rectangular column, openings, holes, unbalanced moments, etc. And some with pre-stressed concrete as well. We have here, of course, to acknowledge a lot of people, some internationals. Professor Paul Regan, it was my supervisor. He was dead, unfortunately, last year, and he helped us a lot. He went to Brazil a lot of times and hosted 4 PhD students for a year. And most of the good idea, let's say, it was thanks to him. I should acknowledge him. Professor Vollum from Imperial College hosted the students as well and helped all these years. Professor Mutoni from PFL in Switzerland and Lausanne hosted one student there. Professor Miguel Fernandez Ruiz hosted students as well, have been in Brazil, all these people, and we have talked, have interacted a lot. Professor Walter Lúcio as well was very important since this time. Of course, as a lot of the Brazilians as well, some of them my ex-students, some colleagues at the same time working together. Because of this, we could have a lot of work, let's say, that could show. And that I should, of course, I have to acknowledge all of them. And here we began in 1995 with an undergraduate student, then some masters, then the PhDs, and we, until now, 2010 here to 17, a lot of PhDs, a lot of masters, a lot of different parameters we studied. And the last ones here, we have tested more than 300 slabs, actually, reinforced concrete, and then pre-stressed more, about 100 here, and it was important. And we did some post-punching as well. I like this picture because how we began, you see, very simple test, just holding at here and a simple check here, pushing the slab. This is the kind of things we had at that time. At the beginning, here's a manual pump. Then, of course, sometime we had some frame, a good frame, quite big actually, and quite strong, because we apply different moments. It has here a kind of helmet that have to hold the column here, hold the column down, and you can apply the moments. Here, a closer view of the frame we have for some time there. And here, of course, you can see the jacks, the actuator, some spreader beams, some, of course, now we have some electronic readings, some load cells, and we have electrical pump. It's not the last type, let's say, the most modern, but works. One of the stirrups we have worked, we have tested, a kind of open one. Here you can see more easily, it is well anchored on top of the flexural reinforcement and go down to the bottom of the slab. You can see here a picture. It goes up here, goes down and goes here. It can be applied after the top reinforcement is in position. This is very good. But of course, we have to guarantee that it can be well anchored, because if it stops here, of course, we will have problem. And of course, should be at the right position, as you have seen. Here's one of the slabs to be tested in another place. Here is one of our students, is Professor Ronaldo Gomez, also supervisor of the student. And quite a big slab here, 3 meters by 3 meters by 200 millimeters thick. And of course, we know that the importance of being well anchored, the reinforcement, the shear reinforcement. Here is a picture. And but what happens if it's not well anchored? Why we are worried about that now, studying this? Because, of course, this is against the good practice, but it can be used as a support for the top flexural reinforcement. And because of this, people is using a lot of this. Top flexural reinforcement becomes easier. It helps grouping series of shear reinforcement. This is one example of a reinforcement that we use usually just as a support of top reinforcement, but there are some people using as a shear reinforcement. Then we tested this and fully anchored at the compression, anchored at the tension, reinforcement, and not anchored at all. Here's the results, and it depends, of course, we're studying this more, but we can see that it's not so different, depending, of course, how is the anchored and how is the level of reinforcement, level of ratio of flexural reinforcement, and the ratio of shear reinforcement. Of course, this should be very carefully studied. Yes. Anyway, and here it's important to see, as I showed, to cut saw. It's very expensive after the test to cut this here, as you imagine, as you have done, but it's very important to do that. Then you can see how the failure surface was in the two sides there. And then, of course, we do a lot of slabs and have a lot of some parameters that we test to investigate, and then we try to make sense at the conclusions, how it behaved. Here is a better view of the upper surface. We did some for rectangular columns as well. At time, it is exactly, this was the first PhD thesis. It was 20 years ago by Daniel. Everything manual at that time, even, but it worked. And we have ACI and another published paper of that, and was very good results. Of course, being cut saw, and then you can see the difference, how it behaved. This student did 15 slabs. Then holes, openings in slabs, very important as well. Some of the shear reinforcement we used here. Some capitals we did as well. Now, we did some tests. I'm doing again now some tests with retreated columns, how this would behave here. Professor Miguel Ruiz is helping us there with the analyzing these results as well. And it's very important. Here's the model we tested. And here some of the results, very important. And then some with eccentricity, how it worked. It's very important as well. Some bubble slabs, bubble deck slabs we tested, pre-stressed. I'm rushing because the time is going. Here, preparation of the slab. studs, pre-stressing. Pre-stressing in lab is very different, it's very difficult to do, and very dangerous. We should take very care. Some failure surface and some results. We did some for edge columns as well. We did some numerical analysis. And to conclude, I would say that research on punching shear and on FRP strengthening, of course, will continue. I will be there around for a couple of years, maybe, or 5 years. But of course, a lot of people is continuing that. New materials displays other possibilities. We are seeing here at the University of Miami a good and big research being done on GFRPs, and we shall prepare a joint project on this, punching with GFRP bars, as Professor Democran in Canada and others are studying. And of course, a sound and comprehensive model to explain how punching shears actually works is still needed. I always challenge the students to find one, a good one for that. I would like to thank again Professor Nani and the University of Miami for having me here for 6 months. And of course, we are trying to have a joint project on punching with GFRPs. And then I should finish now, a little more than 40 minutes. Thank you.